Hey everyone, we're going to be working with two variable absolute value inequalities. So it's going to be a lot like the equations that we were working with when we had two variables and involving absolute value. It's just now we've got absolute value kind of going on right here. So the biggest thing with each of these equations that we want to be able to graph is it's really nice to be able to isolate your y variable, your vertical axis variable. And so with the first equation right here, you can isolate y if you do multiply both sides by 1/2, because the 1/2 times 2 will equal 1, so you just get y on that side. And if you multiply the other side by half, you get 1/2 times the quantity of the absolute value of x plus 6. And then we can just leave it accordingly. So based on what we're seeing right here now with the y isolated, is because you've got the plus 6 right there, that means that you are going to have a horizontal translation 6 units specifically to the left. And then in addition to that, you also have this vertical compression factor by 1/2 right there. So first of all, if I move left 6, we're going to end up having the vertex be located right here, and then it is stretched by a factor of 1/2. So we're going to see the following. And so if I were to graph what I have right there, that right there would be the graph of y values equal to 1/2 of the absolute value of x plus 6 right there. But that's not what we actually want to have graphed, because what we actually want to graph is we want to graph all of the y values that are going to be greater than 1/2 times the quantity of the absolute value of x plus 6. So what that actually does mean for us here is it actually does mean that we don't actually want any of these ordered pairs on the V itself. So I could just keep it dotted like I have, or if I wanted to dash the line, that would be fine. And then it turns out that the y values that are going to be greater are actually going to be above this V shape. So it turns out that I actually want all of these ordered pairs kind of contained like inside of the V shape, but really above the V shape. So of course it's going to really shade forever that way and that way, kind of leftwards and rightwards and upward from there. So that's going to give us all of the xy pairs that satisfy that particular relation that we're seeing there. With this next example here, we actually do have the y isolated. It just happens to be on the right-hand side. It might be nice to put the y on this left-hand side, and so if we do compare it, it does turn out that that left-hand side is greater than or equal to y, which does mean that y is equal to or less than the absolute value of x minus 4 and then minus 5. And so then if we kind of look at this right here, we can see that because we have a subtraction of 4 from x inside that absolute value, that does correspond to a rightwards translation by 4 units, and this right here is going to correspond to a downwards translation of 5 units. So those are the only transformations that are really going to happen. So if I do move to the right 4 and down 5, the vertex of our absolute value graph is going to move there. Now what you're going to notice is that we want all of the y values to equal, but not only equal, but also be lower than. So because of the equal to aspect, when I construct the V shape here, we actually do want the ordered pairs on the V shape right here. And so I actually do want to make a solid line to signify that those ordered pairs are going to be part of the solution set. But now in this particular case, when we've got a less than, then we're actually going to have to shade below the V shape. So it turns out that in this entire sort of region here is going to be kind of our solution set that we're seeing there. With this third example here, we'll have to do a little bit of work to isolate the y variable. So for one, I guess if I subtract 1 from both sides, first of all, we end up getting the following. And then from there, we want to get rid of that negative, so I could divide both sides by a negative or multiply. But since we're dealing with an inequality, right, anytime you multiply or divide both sides by a negative, the inequality symbol is going to have to change direction. So that means that we're going to get positive y is now less than or equal to by switching that inequality symbol. Now the thing is, when I multiply by -1 to the other side, I'm going to have to distribute that multiplication of -1. So this thing right here is really just kind of one single term. So when I multiply by -1, we really get -2, and then this absolute value of x plus 3 is really kind of locked in by those absolute value bars. So that just remains as it is. And then when you multiply -1 to this term right here, you actually now end up getting a +1 right there. So this equation that's in this maroon color here is now solved such that y is isolated, and we should be able to graph this. So we'll notice that we do have an +3 on the inside right there, which will shift the graph left 3 units, and then this will also shift the graph up 3 units. So I'm going to first then identify where that vertex of the V-shape is going to be. And then we also notice that the negative is going to reflect the graph in the x-axis, and we're also going to stretch vertically by a factor of 2. So the graph's going to go upside down and also get stretched by this factor of 2. So it's going to look exactly as I have it graphed and sketched out here. You'll notice then that the y values can be equal to, but then also be lower. So because of the equal to, I can make the line here solid because we can include these ordered pairs, but then we can also shade inside of the V, because inside of the V will correspond to the fact that the y values will be below the graph in this particular scenario. And then this last graph right here, if we were to solve this for y, really I just can undo this addition of the absolute value of x minus 1, that quantity. So by subtracting the absolute value of x minus 1 to the left side, and then by subtracting the absolute value of x minus 1 to the other side, then right there, that's just going to equal 0, so then you're just going to get y on that side. And then you'll have the negative of the absolute value of x minus 1, and then plus 7 on that right-hand side over there. So you'll see that we're going to get a rightward shift of 1 unit and an upward shift of 7 units. So that's going to move our vertex of the V right there. We also have a negative that's going to reflect the graph upside down. So we're going to see that we get the following V shape upside down accordingly. Then we want the y values to be such they are greater than, and so I want to keep the V shape itself dotted or dashed, so I'll just kind of leave it dotted as I have it. And then when the y value is greater than, that means we want to be above the V shape, so all of these ordered pairs here above the V are going to satisfy this particular inequality relationship that we are seeing. And then finally, just going a little bit backwards, you can see we've got a couple of graphs that are constructed with some shading right here, and we are asked to write the absolute value inequality that is represented in each particular graph. So the biggest thing that you'll probably want to find first is where that vertex is located. So in this particular first example, we've got -3, -7 is where the vertex is. So what that does mean is that we'll see the absolute value of x plus 3 when it's shifted to the left 3, and then also a subtraction of 7 to shift it downwards by 7. So we do want to compare the y value to this somehow, because the shading is below the V shape, and then also the line right there is dashed, then we want the y values to be just strictly below this. And then the last element that I want to consider is right in front of that absolute value, whether or not we're going to have any sort of a scalar that we multiply by. So if we do follow the kind of slope of this, you'll see it's just going out a slope of 1. So really, it is just kind of a 1, and it's a positive 1 since the V is facing upwards. So you don't really need to write that 1 right there. So I'll just erase it. It's kind of unnecessary. So it does turn out that that right there is the inequality relationship that is modeled in the graph that we're seeing. And then one more example right here. So like I said, finding that vertex is kind of really important. And so that's got the coordinates 5, -2. What that ultimately means is that because it shifted to the right 5, we're going to see that we have absolute value of x minus 5 for that right shift of 5, and then a subtraction of 2 for the downward shift by 2 units. To compare the y value to this, because the shading is inside the V but really below the V, we want a less than symbol. But then you'll also notice that this border line is solid, which means that we can include those particular points on the border, so we'll want a less than or equal to symbol. Furthermore, you'll also recognize that if we do follow kind of the pattern of the slope of this V shape, you're noticing that it's kind of going down like 5 units and over 2. And so because of that, then we are going to see a negative 5/2 right there. So the 5/2 does stretch the graph vertically by that factor of 5/2 or 2.5. And then that negative, what that ultimately does is, of course, reflects the graph in the x-axis and really just reflects it upside down. So that right there would be the finalized version for that inequality modeling the relationship between x and y that we're seeing in that particular graph.